Good day, everyone. My name is Lawrence A. Cornelio, a AC3 student from Bicol University, Pulangi. And today, I will be discussing about FIR filters. So now, let's look at the code. So, first, for matplotlib. So, for matplotlib, so we use matplotlib use TKAGG set the graphics backend for displaying plots. So, if we import NumPy, matplotlib as matplotlib and several functions from type CPs, which is Perwin, designs the filter. Prerequisite gives us the frequency response, and I L filter applies the filter, and FFT computes the frequency spectrum. So now we create the noisy input. So we set our sampling rate. Fs is equal to 1000 hertz. Then our time vector t goes from 0 to 1 seconds in steps of 1 over 1000 seconds. And so we create a low frequency sine wave at 50 hertz and high frequency sine wave so at 200 hertz with a half amplitude and add random noise. So the noisy signal is the sum of all three components. So we simulate a real world signal corrupted by interference. Now we plot the noisy signal. So we create a figure and plot the noisy signal. So here, let's find the code. So here is the noisy signal. So combination of low and high frequency noise. Now, now we design the FIR low pass filter. So we set our cutoff frequency to 100 hertz. Then we remove frequencies above 100 hertz. So the 50 hertz signal should pass through, while the 200 hertz signal should be blocked. We use num taps is equal to 51. This determines the filter sharpness. More taps give a more sharper cutoff, but require more computation. So the Fourier function designed to filter the coefficients. So now we plot the FIR filters frequency response. So here the frequency response of the FIR filter. Uh, so we use first to compute the filter frequency response, which shows that the filter affects the different frequencies. Now applying the filter to the noisy signal, we use apply the FIR filter to the noisy signal. We use filter signal is equal to I filter to apply the FIR filter to our noisy signal. This function takes the filter coefficient of the signal and outputs the filter signal. So the 1, 0 represents the reference denominator coefficient for an FIR filter, which is always 1. So the filter processes the signal sample by sample, removing the high frequency component. So then we create a figure with two subplots. So the subplots show in the original noise here and the filtered signal. And last is we use frequency domain analysis. So we look at the signals. We look at the signals in the frequency domain using fast Fourier transform or FFT. So one. Okay. So here the top subplot shows the magnitude spectrum of the noisy signal. Let's see the three peaks at 50 Hz from our low frequency signal at 200 Hz from the high frequency signal. and some noise distributed across all frequencies. The bottom subplot shows the spectrum after filtering. Notice at the 200 Hz peak is almost completely gone. The noise floor has been reduced. The 50 Hz peak remains strong. When the filter shows the filter removed the high frequency we wanted to.